Okay, so this is part 2, same thing. The rest of this was Laplace transforms. There is one problem where I give you some functions, and I ask you to find the Laplace transforms. Nothing tricky. I took the tricky one off. There is a partial fraction expansion.
Boo.
What? So there are, no, I didn't do this. I didn't do this. I did do this. And this is possible too. I did not do this. I did do this. Okay. I didn't do this one this time. Okay. So that will help you focus your studying. Finding the Laplace transforms from the tables and the properties, and taking the inverse Laplace transform by doing a partial fraction expansion. Yeah, I didn't do that. I didn't do that. I didn't do that. I didn't do that. I like this one. I always like this one. Calculating power and voltage gain and current gain in dB. That's something engineers do a lot of. I didn't put all this stuff on there. Oh, yeah, wait, we need to take that back. There's a very simple one on there. You may see that, you'll see that in labs. I'm not worried about that. Somebody's yelling at me. Yes, Jordan, use your calculator. If you know how to use your calculator for a partial fraction decomposition, then use it. You're engineers. You got to learn how to use your tools. Yeah, this stuff. I didn't put filters on there because I'm going to get you on that in lab 4. Yeah, so this is the big thing. And there was another thing in here. So we've got pretty much your exam problems. Do a Laplace transform. Do an inverse Laplace transform. Calculate power gain and voltage gain and current gain in dB. And circuits in the S domain. I'd look at that problem on homework, the last homework. Op amps are important. That one. The reason why the one on the homework wasn't fun is probably because I used millifarads and kiloohms or microfarads just to make myself feel better. I used real numbers. I didn't do that on the exam. Yeah, answer those. I didn't do that. So stuff like this. If I had the table, I could do this, but I don't have the table. I got rid of that one. T to the 8, I look at my Laplace transform table, and it says that is T to the N is N factorial over S to the N plus 1. So I just plug in numbers and I get the answer. This one's a little bit more complicated. 10t minus 7 u of t minus 3. So there is a, I don't have my table with me. I took that one off the exam. What did I do? Okay, something like this. If I'm given 5 sine 7t plus 30 degrees, you go to the table, you look up the formula. One thing that I tend to really, I still find a lot of use for is this property that d f of t, because it avoid it. The reason why I like this one is because it makes it so I don't have to do calculus. Actually transforms into s f of s minus little f of 0 minus. So if I ask you to find the Laplace transform of a derivative somewhere on the exam, don't take the derivative. Just transform the function you wanted to take the derivative of, multiply it by s, and subtract off the initial condition. Most of this stuff is just stuff coming from the tables. Partial fraction expansion, you can do it on your calculator, or you can do it by, how much time do I have? Oh, I have time. You can do it by you finding, yeah, okay. So the first thing here is I've got 3 factors in the denominator. I've got s plus 5, and I have s plus 5 squared. So in order to get that lowered, we can get these 2 by residues. But when I try to get this one by residues, if I take f of s and multiply it by s plus 5, this thing goes to infinity and it doesn't work. So the easiest way to do this is residues for a and b and substitution for c. So what I would have to do is I would have to, for that I can't abbreviate it, substitution for c. In order to find that, I would just pick a value. I can't use 0 because 0 makes the denominator go to 0. So I just pick a value. I would find f of 1 on both sides of this equation. That's the easy way to do it. I don't even think I made you complete the square on this exam. I'm getting... Okay, part of the reason why... this is like the first time. I get, there's like 5, 6, maybe more. Depending on how big the class is. This class has been as big as 74 before. I have 8, 9, 10 students in a class like that who never show up for class except for exam day. You guys are amazing. You're showing up for class every day, and I think most of you are showing up for lab. And the lab TA can take 25 points off your lab if you don't show up for lab, even if you turn it in. So that was a warning from 380. Yeah, you guys are doing good. And I think what we really need to do is learn this, because everybody's doing the work. It's just not, I'm not trying to be subtle and tricky. So I used, this is an example where I used residues, I plugged in the value, and then once I get it into this form, I can find the inverse Laplace transform. Do I want to do this one? Yeah, it's in here. So here's one, there was like one like this on the homework where you had to complete the square. They'll all be whole numbers if I make you complete the square. There's the completed square part, and then I have to break it into transformable parts. 2s plus 7 is the same thing as 2 times s plus 2 plus 3. This is the correct form for a cosine, and this is the correct form for a sine. So that's a part that some people have trouble with. And we're not drawing Bode plots. I want to try to get through this. Yeah, I find the most useful Bode plots that you really need to know long term are low pass filters and high pass filters, and maybe understand the concept of band pass filters. A lot of filtering is done now with digital filters, and it's a mathematical kind of software problem. Where you see filters the most is the fact that most semiconductor devices act like filters whether you want them to or not. So if you go into that kind of in that end, and communications people still use it, it's all low pass filters and high pass filters. back when I was in school, we were designing Bessel filters that had like these 6th order Bessel function thingies in there that, yeah, I think, I don't know who does that anymore. There's that one. Filters, know how these filter responses relate. Low pass filter, just like it says, passes low frequencies, blocks high frequencies. This is an ideal response. The real response looks like a simple hole in whatchamacallit, MATLAB, Multisim, or just drawing your Bode plot. We can do this with an R and a C. High pass filters, we just flip the order. Be able to do this, calculate current gain, voltage gain, and power gain in dB. You should know how to do that. Oh, I will tell you right now, circuits in the S domain. If I'm asking you to draw the circuit, there will be no energy in the system at T equals 0. You can kind of just use this model, SL and 1 over SC. You can ignore the sources because they're not going to be in there. I did not make you do this. I did not make you do this. The only people who do linear modeling like that, you'll get to it. You're a power person. Want to solve this one? Somebody said they had problems with this on the homework. I've got like 15 minutes. Or is there something other burning question you want to know about before the exam? Realize some of you are taking this tomorrow.
I had a quick question for the Bode plots.
Yes.
So when we're plotting out quadratic poles, do we take into account the zetas, or do we just approximate?
For a hand-drawn Bode plot, you ignore the snake.
Okay.
When we get to lab 4, in like the 3rd week of lab 4, we design a notch filter that actually uses the snake to make a really steep notch.
Oh, okay.
But it's not something, if you draw the hand-drawn Bode plot of the function, it looks like a straight line.
Oh, okay.
But the snake is what makes it dip.
Right.
But we're only, people who want to do that, look at the effects of the damping. It's called the damping factor. Want to look at the effects of the damping factor. They're using computer models for that because nobody wants to sit there and calculate it by hand. It's too tedious.
All right.
Okay.
Thanks.
Okay, no problem. Anything else, or does anybody want to see? Yeah, you should see this. This is a real circuit, other than the fact that this poor op amp is smoking because it's trying to drive 5 ohms and 1 farad. If you look at their data sheets, they have a maximum capacitance which is much less than 1 farad, and they have a maximum output current which would be just go poof if it had to drive 5 ohms. Okay, but this makes the numbers a little bit easier. So the first thing is that we know this is an inverting op amp because the input is going into the inverting terminal. For an inverting op amp, AV is minus the feedback resistance over the input impedance. Okay, so we have to figure out the feedback impedance. So the feedback impedance is the impedance I see between the output and the negative terminal. So it's those two in parallel right there. So my ZF is ZC in parallel with ZR2, which is 1 over SC times what is R2. R2 is 5. Let's just plug in numbers. C is 1. That makes the math easier. Over, even if it is slightly not really realistic, plus 5. So product over sum. Same thing we learned in 188. Now I've got these improper fractions in here. So to clean that up a little bit, oh no. I'll be back. I know where I'm at.